Alright, hi everyone, welcome back to the channel. This is the 8th video in this dynamic programming series where we are solving the first 16 CSES problems, and we are also developing a general mindset to approach any new DP problem. Now in this video we are going to be discussing this problem grid paths, and not just this, I will be telling you about certain other variations that can be applied on grid problems. Now, again, the aim of this video is not to just tell you the solution of this one problem grid paths. It is to, introduce you to a lot more variations and help you just become better at thinking around these grid problems. With that said, let's talk about grid problems in general. So essentially this is an n cross m grid. And let's suppose I tell you that you are standing on a particular cell I comma j. And let's suppose I tell you that you can only go right and down. Now there could be a lot of different things that you can do with this grid. Somebody might ask you that, okay, let's suppose this entire grid is filled with numbers. Tell me the minimum or the shortest sum path from 0, 0 to n minus 1, m minus 1. This could be one of the problems. Somebody might say that, okay, give me the maximum path, the path that has the maximum sum going from 0, 0 to n minus 1, m minus 1, right? Another variation could be that, okay, this grid does not have any numbers. Tell me the number of paths that can go from 0, 0 to n minus 1, m minus 1, right? These are different type of variations that can be asked to you. So let's see what is happening here. Let's suppose I tell you that this entire grid is filled with certain numbers, okay? This could be any numbers like, 9, 10, 100. All this entire grid is filled with certain numbers. You're standing on this cell 0, 0, okay? And you want to take a path from 0, 0 to n minus 1, m minus 1, this last cell, such that the sum of values on the path that you take is minimum. You can only go right and you can only go down. Okay, let's try to solve this problem first of all. We are not looking at the problem grid paths that is there in CSES. We are first of all developing a general mindset behind these grid problems. Okay, so starting from 0, 0, you want to get to n minus 1, m minus 1 in the shortest sum path. How do you do this thing? So initially, if you look at it, the biggest problem that you're trying to solve is going from 0, 0 to n minus 1, m minus 1. Correct? Now understand this problem like this. You have two directions in which you can move. One of the directions is that, okay, you can go right, and the other direction is that you can go down. When you go right, what happens is that you go from 0, 0 to something like 0, 1. If you go down, you're going to 1, 0. Now look at this entire thing and consider the sub-problem size. Initially, you had to go from 0, 0 to n minus 1, m minus 1. Now the sub-problem reduces. Initially, you were concerned about this entire grid, right? Now, if let's suppose you move to this direction towards the, let's suppose right direction, then you're only concerned about the grid from here to here, right? Clearly, we can say that the size of the grid is reducing. So if you move towards the right, the sub-problem size is going to reduce, correct? Similarly, if you go down, the grid reduces to this. So when you go from 0, 0 to any of these two cells, the sub-problem size reduces, right? And similarly, if you try to look at the overlapping sub-problem idea here, there are two paths which will, have the exact same sub-problem. Let's suppose you went from here, this yellow one, and then you came here, okay? This is one of the paths that you could take. Let's suppose you took another path, this orange one, you went down first and then you came here, right? Now look at the problem starting from this cell, this green cell. Can I say the sub-problem is same in both the cases? First you came here, then you're concerned about this entire grid, right? In the next one, you did this and then again you're concerned about the same grid, right? So overall, this sub-problem is the same in both of these cases. So there are essentially going to be a lot of overlapping sub-problems. So it does make sense to store the answer of one sub-problem and use it again and again, correct? Now let's try to understand some variations. You're standing at 0, 0. And in one of the cases, you went to 1, 0, and the other case you went to something like 0, 1, right? Now, this entire sub-problem, we were trying to solve this thing, okay? Minimum sum path from 0, 0 to n minus 1, m minus 1. This was the problem that we were trying to solve, okay? So we said that, okay, this problem breaks down into smaller sub-problems. And we can say that, okay, if this thing tells me the smallest sum path from 1, 0 to n minus 1, m minus 1. Let's suppose this value comes out to be 100. Okay, the path sum from 1, 0 to n minus 1, m minus 1. Let's suppose this path sum comes out to be 200. Okay. Then you clearly know that this is a better choice right here. This is a better choice. So what would you say? You would say that, okay, the minimum sum path for 0, 0 is nothing but 100 plus whatever is the value present at 0, 0. So standing at any cell I, j, I know for a fact that I can either go right or I can go down. So if I am concerned about this subproblem, the minimum answer for this subproblem, which is like saying what is the minimum sum path from I, j to n minus 1, m minus 1. How will I find it out? I will say that, okay, one of the possibilities is this. Consider the path here, the best one. Okay, let's call it x. Then another possibility is here. Consider the path here. Let's call it y. Just choose the minimum of them. Just take minimum of x, y. And then just do one thing, just add this value. Whatever is the value present at I, j, you just add it to the total sum and that will give you your answer for I, j. Correct? So can I write my DP state like this? DP of I, j is equal to minimum sum path from I, j to n minus 1, m minus 1. Right? I also know that, okay, if this is a bigger subproblem, what are the smaller subproblems into which it is going to break? One of the smaller subproblems is DP of I plus 1, j because we are going down. Another subproblem is DP of I, j plus 1 because we are going right. So I also know the relation between these, subproblems. Basically, I'm just going to take the minimum of them and then I'm going to add the value that is present at my current node, right? So can I say I also know the transition? DP state is fine. I also know the transition that DP of I, j is equal to minimum of these two values, which is DP of I plus 1, j and DP of I, j plus 1. And then what I'm going to do is I'm just going to add my current value to it, which is, let's define this entire grid with the variable grid. So I can just say add grid ij to it. Yes, this is going to be my transition. Correct? Now, what is going to be the base case here? Clearly, if I reach the end here, when I reach the end, there are going to be no more transitions, right? You are not going to be breaking into any more subproblems. So can I write my base case would be DP of n minus 1, m minus 1 is simply equal to whatever is the value present at that particular cell, right? Now you could also say that these are also base cases. That, okay, this entire column is a base case. This entire row is a base case. You could also say this, but there is no need to say this. What you can say is that when you are in a cell in the last row, you will not consider the possibility of going down. You will only consider the possibility of going right. Okay, this is what you can say. You can just add simple if statements. So what I can say is that if this was the state, if this was the transition, the base case would be this. DP of n minus 1, m minus 1 is equal to simply grid of ij. Grid of n minus 1, m minus 1 rather. Correct? What is going to be our final subproblem? What was that initial problem that we were solving? We wanted to go from 0, 0 to n minus 1, m minus 1. So the final subproblem is the minimum sum path from 0, 0 to n minus 1, m minus 1. Right? So let's write the final subproblem also. Final subproblem will be DP of 0, 0. Now think about a variation. Let's suppose I ask you that, okay, don't tell me the minimum, tell me the maximum. Can you still do it? Yes, because then you will just change this transition from minimum to just maximum. Correct? So this variation is done, right? This thing. If you had to find out the maximum or the minimum sum path from 0, 0 to n minus 1, m minus 1, we are done. Correct? Now let's talk about this thing. Number of ways. How do you find out the number of ways to go from 0, 0 to n minus 1, m minus 1? Let's consider that. If I have this as the grid, and let's suppose I know that from here, going to n minus 1, m minus 1 has, let's suppose, 100 ways. So 100 ways are there to go from 0, 1 to n minus 1, m minus 1. And I know there are, let's suppose 300 ways to go from 1, 0 to n minus 1, m minus 1. How many ways are going to exist for this particular cell? Clearly, it has two subproblems, right? One of them takes 100 ways, the other takes 300 ways. So I can just simply say that in this case, I will not be taking minimum or maximum of these two subproblems. I will just add up their answers. So this is the problem that we are solving. Number of ways now. Number of ways to go from 0 comma 0 to n minus 1 comma m minus 1. Okay. Now what we can do is we can define a similar DP state for any cell I comma j. We can say that, okay, the number of ways to go from I comma j to n minus 1 comma m minus 1, define it as a DP state. So let's define the DP state here. DP of I comma j is equal to number of ways to go from I comma j to n minus 1 comma m minus 1. Correct? Now what is going to be the transition? Obviously you have two smaller subproblems, I plus 1 comma j and I comma j plus 1. So I can just simply say that the transition is going to be this. dp of I comma j is equal to dp of I plus 1 comma j, which is the case where you go down, plus dp of I comma j plus 1, which is the case in which you go right. Yes. So essentially this is how it works in most DP problems. When you have to find out the number of ways, you just add up all the ways of the smaller subproblems. When you have to find out minimum or maximum, you just take the minimum or maximum. As simple as that, right? So this is the state. This is the transition. The base case would be very simple. When you reach the end at dp of n minus 1 comma m minus 1, the answer is going to be just 1. There are no more ways to, break it into a smaller subproblem. So base case is also pretty clear that it is going to be dp of n minus 1 comma m minus 1 is equal to 1. Just one way to go from n minus 1 comma m minus 1 to n minus 1 comma m minus 1. Final subproblem is also very clear, right? Final subproblem is simply going to be the number of ways to go from 0 comma 0 to n minus 1 comma m minus 1. So final subproblem is dp of 0 comma 0, right? So we've looked at three variations here, right? We've looked at minimum maximum. How do you find the minimum maximum path from 0 comma 0 to n minus 1 comma m minus 1? We've also looked at number of ways, right? And we've seen a very obvious DP state here. It is not some, magical stuff that we're doing here. All of these things are very, very logical. Now think about one more thing. Right now we thought of a DP state like this, that we will go from any cell I comma j to n minus 1 comma m minus 1. This is the way in which we were thinking, right? From I comma j to n minus 1 comma m minus 1. Somebody could have also thought of a DP state like this, that go from 0 comma 0 to I comma j. Is that going to be wrong? No. See, here we defined a state like this. Number of ways to go from I comma j to n minus 1 comma m minus 1. Somebody could have said that don't consider this state, but rather consider a different state, that going from 0 comma 0 to I comma j. What are the number of ways to go from 0 comma 0 to I comma j? This is also going to solve the same problem. But overall, the way of looking at this problem is a bit different. And now we can't say that it is wrong. Even though the states, the parameters in the states are going to be exactly same, the meaning of the state is different. And let's see how that changes the entire problem. So let's try to solve that same problem. Finding out minimum path from 0 comma 0 to n minus 1 comma m minus 1. And now let's define a DP state like this, that instead of going from I comma j to n minus 1 comma m minus 1, I will try to come to I comma j from 0 comma 0. Yes, so let's define a DP state like this. dp of I comma j is equal to minimum sum path from 0 comma 0 to I comma j. Now remember, this is a different DP state even though the parameters are same. See, ij, we are using the exact same parameters, but the meaning of the state is different. Okay, so unless and until you define the meaning of the state, it doesn't make a sense. Now let's try to see how does this problem, work out. Clearly, if this is the grid, you're standing at, or you're coming to I comma j from 0 comma 0. So what are the two different ways in which you can come to I comma j? You can either come from top, because the top cell is allowed to go down, or you could come from the left because the left cell is allowed to go right. Correct? So now if you look at it, we are talking about coming from 0 comma 0 to I comma j, right? So we will also have to talk about how can you reach I comma j. So can I say the two subproblems for I comma j here would be not I plus 1 comma j and I comma j plus 1, but rather they would be I minus 1 j and I comma j minus 1, right? So you want to come to I comma j, right? So can I say dp of I comma j, we want to consider the minimum sum path. So we will say minimum of these two possibilities, whichever path comes as the minimum. See, if you take this one, this is dp of I minus 1 comma j. This is going to mean the minimum sum path from 0 comma 0 to I minus 1 comma j. So one possibility is dp of I minus 1 comma j, and the other possibility is this one, okay, this one, where you go from 0 comma 0 to I comma j minus 1, right? So you consider both these possibilities and then you just add up your current value, which is going to be grade of ij, right? Now you see how this same problem, we defined the state in a different way and we got two different transitions, all right? And even the base case here is going to be different, because the base case would be just this, okay, that going from 0 comma 0 to 0 comma 0, what is the minimum sum path? That is going to be the base case. And the final subproblem will also change now. The final subproblem will be dp of n minus 1 comma m minus 1. What is the minimum sum path to go from 0 comma 0 to n minus 1 comma m minus 1? Correct? So let's write the base case here as well. The base case would be simply dp of 0 comma 0 is equal to grid of 0 comma 0. Okay. And finally, the final subproblem, let's also write it here. That is going to be just dp of n minus 1 comma m minus 1 now. Okay. So we've looked at certain things here. First of all, the importance of state, transition, all of these things. Secondly, we've looked at three variations of the same problem, the grid problem, right? Now let's look at one more variation, which is actually the variation being asked in the CSES problem set, okay? So this variation is this. Let's suppose your entire grid had certain obstacles, and now you want to find out the number of ways in which you can avoid these obstacles and reach the end, right? Let's see. Let's consider the same grid. And let's suppose I tell you that, okay, there are certain obstacles. This is the same problem in the CSES problem set that we are solving now. So let's suppose these are obstacles. Okay, you cannot come to these orange cells. So now tell me the number of ways to go from 0 comma 0 to n minus 1 comma m minus 1, or tell me the maximum sum path to go from 0 comma 0 to n minus 1 comma m minus 1. All of them are the same problems. Now all you have to do is just make sure that you don't end up at an obstacle. How can you do this? Let's suppose we were talking about minimum sum path. We want to find out the minimum sum path to go from 0 comma 0 to n minus 1 comma m minus 1, avoiding these obstacles. All you have to do is that for these particular cells, you can just define the dp state to be pretty huge. Like you can say that dp of, we are using that same dp state, okay? Let me first define it. Minimum sum path to go from I comma j to n minus 1 comma m minus 1. We are using this particular state, okay? So essentially this depends on dp of I plus 1 comma j and dp of I comma j plus 1, all right? What you could do is that whenever you end up at an obstacle, like this is an obstacle, right? This orange one, this is an obstacle. So you can say that for these obstacles, clearly you want to avoid them, right? So there is no path to go from these obstacles to this cell n minus 1 comma m minus 1. You can just simply say this, dp of I comma j is equal to infinity if I comma j is an obstacle. If you do something like this, it will make sure that you don't consider this path in your minimum or the shortest sum path. And you can finally say that, okay, if the minimum sum path to go from 0 comma 0 to n minus 1 comma m minus 1 comes out to be infinity, then it doesn't have a valid path. If it comes out to be a value lesser than infinity, then you know that there is at least one path. Now, one more thing, everything else is going to be the same. The state, the transition, the base case, the final subproblem, everything else is going to be same. It is just one clever thing that we've done here, that for the obstacles, we've defined that, okay, dp of I comma j is equal to infinity, so that you never consider that one path, okay? And now one more thing, let's suppose you were asked that, okay, instead of minimum, tell me the maximum sum path. What would you do? You would just simply say that, okay, dp of I comma j is equal to minus infinity, because you don't want to consider that path. Now let's suppose somebody told you, don't find out minimum or maximum, find out the number of ways. What would you do now? You can just simply say dp of I comma j is 0, because, you know, dp of I comma j is equal to 0 just means that there are no ways to go from I comma j to n minus 1 comma m minus 1, correct? So I think this should be very clear now, right? This thing, avoiding obstacles. And this is the same problem that has been asked in the CSES problem set. We are going to look at some more variations of grids, and that is going to open up your mind even more, okay? So I hope this is clear. How do you avoid obstacles and how do you solve for these same three problems? So now let's talk about this one problem, which is also very interesting. So let's suppose I told you that there is one particular checkpoint in this entire grid, and you want to find out the number of ways which actually go through this checkpoint, that you must go through this checkpoint in order to go from 0 comma 0 to n minus 1 comma m minus 1. How do you solve this problem now? So what you must observe here is this. If you look at this grid, okay, if you look at this green grid, And if you look at this orange grid, okay, these are subgrids of the same grid. Let me color them. This orange grid and this green grid. If this is the cell that you're talking about, this particular green cell, or this whatever color is this, white, let's suppose. If you're talking about this cell, the number of paths which go through this cell, how do you find out this? That's the question. Can you think about it like this? First of all, there are three variations again. Finding out minimum sum path, finding out maximum sum path, and finding out number of ways. So let's try to first of all find out for minimum. Okay. So what we can do is that if we want to go through this cell, we can just say that, okay, from 0, 0, you must come to I, j, whichever cell this is, this one, right? And then we can say that you have to go from I, j to n minus 1, m minus 1. So if I say that, okay, the minimum sum path to go from 0, 0 to I, j is, let's suppose, x, and the minimum sum path to go from I, j to n minus 1, m minus 1 is y. Can I simply say that the minimum sum path that goes from this checkpoint I, j is simply going to be equal to, first of all, the minimum of this, secondly, the minimum of this, and you take the overall minimum of these two quantities. Can I say this? Yes. So my overall answer here would be simply minimum of x, y. Now, one more thing here, which is very important, is that now these are two different problems that you're solving. Earlier, we were just concerned about going from 0, 0 to n minus 1, m minus 1. So the very first state that we defined was dp of I, j is equal to minimum sum path to go from I, j to n minus 1, m minus 1. This is how we were looking at it. Now in this problem, we need to look at both the states, right? So we defined two different states so far. Remember, one of the states was going from I, j to n minus 1, m minus 1. Another state was coming from 0, 0 to I, j. So what you would do is you would make the use of both of these cases. In first problem, which is problem 1, you are trying to solve for going from 0, 0 to any I, j. Second problem is you are trying to solve for going from I, j to any n minus 1, m minus 1, right? So let's define our states like this now. dp1 at I, j is equal to minimum sum path from 0, 0 to I, j. Yes. And let's define another dp state like dp2 of I, j is equal to minimum sum path from I, j to n minus 1, m minus 1. Now we already know the transitions for both of these cases, right? We know the base cases, we know the final subproblems as well. We have solved both of these problems just now. So what is going to be our final answer now? We want to go from 0, 0 to I, j. We know its value. We want to go from I, j to n minus 1, m minus 1. We also know its value. So can I say my final answer will be just this one? Like there are two things. You want to go from 0, 0 to I, j. So let's define the checkpoint coordinates as ci and cj. So I will say dp1 of ci and cj and dp2 of ci and cj, right? So essentially we looked at two different states here. We want to go from 0, 0 to I, j. We want to go from I, j to n minus 1, m minus 1. We are going to be solving these two states differently, okay, independently. First, you are going to calculate dp1 of I, j. Then you are going to calculate dp2 of I, j for every single I, j. Okay. So essentially you solve these two problems independently and finally your answer will be this. Okay, the given checkpoint that is present. So I hope this problem was a bit more interesting than the problems that we've covered so far, because here it is not just about thinking about a random state and solving this problem. Here we are using two different states in the same problem. Okay, and it becomes absolutely very important to define what is the meaning of the state. Unless and until you define the meaning, it will not make sense. Got it? So we've looked at how we can go from 0, 0 to n minus 1, m minus 1 such that it includes a checkpoint and it has the minimum sum path. What about the number of ways? How do you find out the number of ways now? See, it's also very obvious. Let's suppose I told you that the number of ways to go from 0, 0 to I, j is 16. Let's suppose I told you this thing is 16. And let's suppose I told you that the number of ways to go from I, j to n minus 1, m minus 1 is just, let's suppose, 3. Can I say the total number of ways which include this checkpoint is simply going to be 16 into 3? Yes. So the same thing follows. You will just multiply both of these DP states to get your answer for this checkpoint. Alright. So yes, that was the variation considering one checkpoint. Now let's solve the problem which is the big daddy here. Multiple checkpoints. Let's suppose you have multiple checkpoints in the grid. You want to cover every single checkpoint. Find out the number of ways to go from 0, 0, covering every single checkpoint, to n-1, m-1. Let's suppose these are the checkpoints that you want to use, okay? How are you going to find out the number of ways which go from 0, 0 to all these checkpoints and then lands up at n-1, m-1? How are you going to do this problem now? First of all, the very basic observation here is that you cannot go to this checkpoint and then expect to come to this checkpoint. This is not going to happen, right? So essentially what is happening here is that every single checkpoint, if you look at it, it has a relative order when you look at 0, 0 and that checkpoint. Obviously, if you define these checkpoints as, let's suppose C1, C2 and C3, C1 has to be reached first and then you can go to C2 and then you can go to C3. Now you could also think of an example like this, that what if you have these checkpoints? There is going to be no path which includes all of these checkpoints. No path which includes all of these checkpoints, okay? Because it's pretty obvious, right? If you have to get to this checkpoint, you can only go to this checkpoint like this. Once you come to this checkpoint, you are only left with this grid. You cannot come to this checkpoint, right? So essentially, obviously the answer might be that it is not possible. But let's assume you are given these checkpoints where the answer is always possible. You want to still find out the number of ways to go from 0, 0 to n-1, m-1, including all these checkpoints. How do you do this now? Okay. The very first thing that I told you is that every single checkpoint is going to be having a relative order. Okay. How can you define this relative order? The farther the checkpoint from 0, 0, the later you will have to reach it. Okay. Look at this cell. This cell is the nearest to 0, 0. So this is the first checkpoint that you have to encounter before you can go to other checkpoints, right? So this is pretty obvious. You can define a distance thing that, okay, which checkpoint is closest to 0, 0, I will have to reach that checkpoint first. So first you're concerned about this grid. Number of ways to go from 0, 0 to this checkpoint. And let's remove this checkpoint because it is not going to allow any possible path. So first we've understood that we've gone from 0, 0 to this C1. Okay, let's define this number of ways to be x. The number of ways to go from 0, 0 to C1 is x. Now, obviously you want to go from C1 to C2 now, right? So the relative order has to be first of all maintained. Okay, you will have to sort all of these points based on the relative distance from 0, 0. Okay, once you're done with that, then it is all about saying that, okay, you want to go from 0, 0 to checkpoint 1, then from checkpoint 1 to checkpoint 2 and so on. Okay, so let's suppose now you look at C1 and C2. So you are concerned about this grid, right? Let's call the number of ways here as y. Number of ways to go from C1 to C2 is y. Okay. Now, if you look at this thing, this C3, you want to go from C2 to C3. So this is a different grid now, right? So if you look at these mini grids that are being formed, okay. First, you want to go from 0, 0 to C1, okay. So this is what you want to do. Next, you want to go from C1 to C2, okay. Let's pick up a different color. Right? Next, you want to go from C2 to C3. And then from C3, you want to go to the last n-1, m-1. So this is the only grid that will be left. If you look at this problem now it would make sense that, okay, if this going from 0, 0 to C1 takes x ways, going from C1 to C2 takes y ways, going from C2 to C3 takes z ways, and let's suppose this takes a ways. Overall, the number of ways to go from 0, 0 to n-1, m-1, encountering all these checkpoints is simply going to be x multiplied by y multiplied by z multiplied by a. Okay. Now, one thing to note here is that you will have to solve these mini grid problems. Okay. Even first of all, you were concerned about this big grid. Now what we are saying is that we have these checkpoints. So we are concerned about these mini grids. Okay. We have to solve these mini grids differently. So yes, now let's come back to our grid paths problem that was there on CSES. And now you will see how easy of a problem this is, considering the entire stuff that you have learned right now. Okay, so let's read this problem statement. Consider a n cross n grid whose squares have traps. It is not allowed to move to a square with a trap. Your task is to calculate the number of paths to go from upper left corner, which is 0, 0, to n-1, m-1, such that you don't encounter any of these traps. Same problem that we had looked at, you have to avoid the obstacles. So let's consider the example that has been given to us. So it's pretty obvious, like if you look at it, let's try to find out some ways One is to go from here to here. This is one way, right? Another way could be that, okay, you go from here to here. This is one more way. Another way could be that, okay, you take this path. So essentially there are three paths, which is also the answer for this problem. Now, obviously, it's a pretty easy problem considering what we have already looked at. We can simply define our DP state now. We can say that, okay, DP of ij is equal to number of ways to go from I comma j to n minus 1 comma m minus 1. Correct? This is what we can write. The transitions are pretty obvious. From I comma j, you can go to I plus 1 comma j and I comma j plus 1. So the transition could be this: dp of I comma j is equal to just dp of I plus 1 comma j plus dp of I comma j plus 1. Correct? This is what we can write. Now, in terms of the base case, it is obvious. Once you reach the end, when you reach n minus 1 comma m minus 1, the number of ways to go from n minus 1 comma m minus 1 would be just 1. But obviously one caveat here is that the last cell could also have an obstacle. Okay, so if it has an obstacle, then we'll just say that, okay, dp of n comma n minus 1 comma m minus 1 is equal to 0. And obviously here the only coordinate that is given to us is n. We are not given an n cross m grid. We are rather given an n cross n grid. So it doesn't really matter. The base case here would be just this: dp of n minus 1 comma n minus 1 is either equal to 1 or is equal to 0. It is equal to 0 when it has an obstacle, when n minus 1 comma m minus 1 has an obstacle, and this is the case where you don't have an obstacle. All right, this is the base case. Final sub problem is very obvious: dp of 0 comma 0, number of ways to go from 0 comma 0 to n minus 1 comma n minus 1. Correct? Now, like I said, if you have an obstacle, for that particular cell, you cannot go from that cell to n minus 1 comma m minus 1. So you will have to make sure that when you're doing this transition, this one, dp of I comma j is this. If your I comma j has an obstacle, then you need to make sure that your dp of I comma j is 0. Number of ways to go from I comma j to n minus 1 comma n minus 1 is 0. All right. So let me write it again here. This was the state. This was the transition, with obviously an if statement that if the cell contains an obstacle, then dp of I comma j is going to be 0. This was the base case. This was the final sub problem. Okay. So before we actually look at the solution, let's try to look at the time complexity. The time complexity is pretty obvious. The number of states are n into n square states, and the number of transitions are just 2. So the transition time is just going to be order of 1. So time complexity. Now again, guys, we are not going to be having the same pace like the first class. The pace is going to increase. Okay, so you will have to make sure that you're watching the videos in this series in the same order. All right, don't just jump into a random video and expect to understand everything from that video. All right, so time complexity is simply going to be equal to order of n square, because you have n square states and transition time is just order of 1. Same is going to be the space complexity, because the states itself are n square, right? So space complexity is also going to be order of n square. Fine. Now let's try to see how would you actually code it up, right? Like obviously we're not going to go into the mindset of first of all thinking about recursive solution, then iterative, then all of these things. We are directly going to think how do you code it iteratively. Okay. So see, if you were to look at the cell I comma j, it depends on the cells I plus 1 comma j and I comma j plus 1. So if I fill my dp values in this order, that first of all I calculate this value, the answer for this dp state, then for this, then for this, then for this, then for this, it will work. Then if I calculate these states, then if I calculate these states, then if I calculate these states, I will make sure that for any given cell I comma j, the cells on which it is dependent, they have already been computed. All right. So now let's look at the code for this problem. So first of all, this is the grid that I have taken. I have defined it as an array of strings, because obviously here in the problem we have been given dots and asterisks, right? So whenever there is a dot, we say that it is an empty cell. Whenever there is an asterisk, we say it is a cell with a trap or an obstacle. Fine. So this is the dp state that we define. dp of ij is equal to number of ways to go from I comma j to n minus 1 comma m minus 1. This is the base case, like I said. So dp of n minus 1 comma n minus 1, the last bottommost cell, is going to be equal to 1 if that cell doesn't contain an obstacle. So basically the number of ways to go from the last cell to the last cell itself is 1 if it is not having an obstacle. But if it has an obstacle, then obviously you cannot go from that cell to that cell if that has an obstacle, right? So in that case, it is equal to 0. Cool. And finally, this is the transition step. Here, like I said, we will have to have a particular order in which we write the for loops. I've already told you how to iterate. You first of all fill the last row from right to left, then you fill the second last row from right to left. Okay. And obviously the rows are going to be going from bottommost to the top, right? So here, this I defines the row, this j defines the column. So column also we're going to go from right to left. Okay. So this was the base case which we had already calculated. If I is equal to n-1 and j is equal to n-1, then we've already defined the DP state for that. So for that, we will just continue. And obviously, like I said, if that cell contains an obstacle, the number of ways to go from that cell to the last or the bottommost cell is 0. Otherwise, you have two possibilities. One is that you go right and the other is that you go down. Okay. So in the first possibility, we are going down, but we can only go down provided there are cells available in the next row. So here what I'm checking is that if we are not in the last row, then consider this possibility. And similarly, if we are not in the last column, then consider this possibility of going right. Cool. And then finally, we just add them and take the mod as it is required in the problem statement. And finally, we print this final subproblem. Okay. So I hope this entire problem is clear to you. And there is one more caveat that I would just like to talk about, which is the space optimization concept. Okay. So if you look at it, you know for a fact that this particular cell I, j, it depends on two cells. First is the cell towards its right, and the second is the cell towards, just the cell lower than that cell, right? So can I say in order to calculate the answers for this entire row, this pink row, I am just dependent on the answers for this white row. Can I say this? I don't need these further rows anymore. So I can do a space optimization here as well. To calculate the answers for a particular row, I will just use the answers for the next row, and then I will not care about the rows after that. Okay. So I can show you the code for that as well, but I would expect you to, try this out on your end first of all, and then only look at my code for space optimization. Okay. So this is the code for space optimization. Obviously, the space is going to reduce from order of n square to just order of n, because now we will have to maintain one row in memory at any given point of time. So first of all, here I am defining, the answers for the last row. For the last row, can I say that, okay, if you're at the bottommost cell and at the rightmost cell, then the answer is going to be either 1 or 0. That is the base case. It is going to be 1 if it does not contain an obstacle. So this one. And if it contains an obstacle, then it will be 0. And then here what I'm doing is I'm first of all filling the last row completely. Okay, I'm first of all filling the last row completely. And then beyond that, all I'm doing is that I'm just filling up the rows going above. Like I filled the last row, then I go to the second last row, then I go to the third last row, then the fourth last row, and so on. Right? So here I am defining my current row. Current row here simply means this. Current row at j is simply equals to dp of ij. Like we have defined dp of ij in the previous implementation, it is simply equal to that. And next row at next row at j is simply equal to dp of I plus 1 comma j. Okay, just remember this thing. Fine. Then eventually this is what we're doing. Again, same case. If it is an obstacle, then current row at j or dp of ij is equal to 0. Otherwise, I consider two possibilities. One where you go down, next row at j. One where you go right, current row of j plus 1. Finally, we find the answer for our current row. And then at the end, we just update our next row with the current row. Got it? This is what we've done in the space optimization lecture already. Okay. So if you haven't watched that, I would highly recommend to go and watch that, and you will be able to understand this concept pretty easily. Okay. And finally, we print the answer as next row of 0, because next row eventually is going to contain all the DP zeros, the answers for the topmost row. Okay. So yes, guys, that is it for this problem. And I hope you learned a lot from this lecture. You would have opened this video considering that you would only learn about this one problem from CSES, but overall you would have learned a lot more variations, and your thinking around these grid problems or thinking around DP would have become much more better now. Okay. So in case you haven't subscribed to this channel, be sure to subscribe and press the bell icon to not miss any future updates on this series. And secondly, if you've understood every single thing that was taught in this lecture, don't forget to comment understood, in the comment section, and that would give me a lot more motivation to continue making more videos. Right. So yes, that is it. I will see you in the next video.